Hello and welcome to this comprehensive tutorial on designing helical antennas and quadrifilar antennas. I'm excited to have you here as we dive into the fascinating world of antenna design. In this tutorial, we'll start by exploring the theoretical principles behind these antennas, including their modes, geometrical configurations, and impedance characteristics. Then, we'll move into the practical side by using CST Studio Suite to design and simulate these antennas step by step. Whether you're a beginner or have some experience with antenna design, this video will guide you through the process in a clear and approachable way. By the end of this tutorial, you'll have the knowledge and confidence to create and analyze your own antenna designs. So, grab a cup of coffee, sit back, and let's get started with this exciting journey into antenna engineering. Helical antennas are a type of wire antenna that consist of a conducting wire wound into a helical shape. These antennas are widely used due to their versatility, compactness, and high-gain properties, making them suitable for applications such as satellite communication, GPS systems, and space exploration. The design of helical antennas allows them to operate efficiently across various frequency ranges depending on their physical and geometrical configuration. Helical antennas primarily operate into modes based on their geometrical and electrical properties. 1. Normal mode, resonant mode. In this mode, the helical antenna's dimensions are much smaller than the wavelength of the operating frequency. The radiation pattern is omnidirectional, similar to a dipole antenna, with the maximum radiation occurring perpendicular to the helix axis. Normal mode is suitable for compact, low-gain applications such as mobile communication devices or RFID tags. 2. Axial mode and fire mode. In axial mode, the helix dimensions are comparable to the wavelength of the operating frequency. The antenna radiates along its axis, producing a directional beam with high gain and circular polarization. This mode is ideal for satellite communication and radar systems. This slide shows a figure of a helical antenna. The performance and characteristics of a helical antenna depend on key geometrical parameters, pitch angle or alpha. The pitch angle determines the slope of the helix and is given by the shown formula, whereas is the spacing between adjacent turns of the helix. The total number of turns in the helix determines by an parameter. Another parameter for a helical antenna is wavelength. The operating frequency is directly related to the wavelength and can be calculated by the given formula. Next parameter is helix circumference. The circumference plays a critical role in determining the operating mode. For axial mode, C is typically about 0.8 to 1.2 of wavelength. A common configuration for feeding helical antennas involves using a coaxial feed with a matching network to transform the impedance to 50 ohms, typical for most RF systems. Using a balloon or a balance-to-unbalanced transformer to ensure proper impedance transformation is another technique. In this slide's parameters for designing a helical antenna with CST Studio Suite is provided. A quadrifilar antenna, also known as a quadrifilar helix antenna or QHA, is a type of antenna that consists of 4 conductors, arranged in a specific geometric configuration, which is typically helically wound. These antennas are widely used in applications that require circular polarization and wideband performance, such as satellite communications and GPS systems. The quadrifilar antenna is designed to produce a circularly polarized radiation pattern, which makes it especially suitable for communication systems where the signal needs to be received from various orientations, such as in satellite communications. The 4 elements of the antenna are typically wound into pairs of orthogonal helices, with each pair of elements typically offset by 90 to ensure the desired polarization. The input impedance of a quadrifilar antenna is primarily influenced by its geometry, including the following factors. Diameter of the helices. The diameter of the helix elements affects the impedance. Larger diameters generally lead to a lower impedance, while smaller diameters result in a higher impedance. Pitch angle. Similar to helical antennas, the pitch angle of the quadrifilar helices affects the impedance. The angle typically lies between 15 and 30 degrees, and the specific angle impacts both the impedance and the radiation pattern. Element spacing and length. The physical length of the helices and their separation also influences the impedance. In general, a quadrifilar antenna with more turns and longer elements tends to have a higher impedance. The input impedance of a quadrifilar antenna usually falls in the range of 50 to 150 ohms, but 100 ohms is a typical design target. The exact impedance depends on the antenna's design and the characteristics of its feed mechanism. Resonant impedance. Quadrifilar antennas are often designed so that their impedance matches a 50 ohm transmission line, the standard for most RF systems. However, matching is crucial for efficient power transfer, and various techniques like impedance matching networks or the use of balloons are often employed. Coaxial feed. The most common feed for quadrifilar antennas is a coaxial cable. A balloon-balanced to-unbalanced transformer is often used to feed the antenna in a way that ensures both pairs of helices are properly excited. Impedance matching. As with other antennas, impedance matching is essential for efficient power transfer. A quarter-wave transformer, tapered transmission line, or lumped element matching network can be used to match the impedance of the antenna with the system's transmission line, usually 50 ohms. At the end of this slide, design parameters for a quadrifilar antenna is provided as you see. Now that we have covered the theoretical aspects of the helical antenna, including its modes, characteristics, and mathematical formulations, let's move on to the practical part of the tutorial. We will start by setting up a new project in CST, defining the geometry of our helical antenna, and specifying the material properties. Then, we'll set the feed structure and apply the necessary boundary conditions to simulate the antenna's performance. Once our model is ready, we'll run the simulation to analyze the impedance, radiation pattern, and other key parameters that define the antenna's efficiency and performance. Let's get started with CST and move from theory to hands-on design. I'll guide you step by step, so don't worry if you're new to the software. Follow along and you'll be able to simulate your own helical antenna in no time. To begin, open CST and start a new project. Select the microwave and RF optical template, then choose antennas followed by wire. For this analysis, we'll use the time domain solver. Click Next. Now, let's set the frequency range from 1 GHz to 3.5 GHz, which covers our frequency of interest. Once that's done, click Next and then Finish to create the project. The first step in our design is to add the structural parameters to the parameter list section. This helps us keep track of all dimensions in one place. Next, let's define the helical shape. To do this, go to Macro, select the Construct option, and then choose Coils. From here, select 3D Linear Helical Spiral. You'll see several options appear. Options 2 and 3 represent the helical radius in 2 orthogonal dimensions, which will be the same for our helical antenna. The next option sets the height of the helical structure, and after that, you can define the number of turns. In this section, you can also select whether the antenna should be clockwise or anti-clockwise for circular polarization. For our design, we'll use the clockwise option to achieve right-hand circular polarization. Click OK to create the 3D helical shape. Once the shape is created, go to the parameter list and replace the default values with your desired parameters. Pressing F7 will update the structure. Now, you should see a helical shape with the parameters we defined. Currently, the shape is just a wire without any thickness. Let's fix that. Go to the Curves menu and select Circle. Define a circle according to the desired parameters. Then, go to Create Shape from Curves and select the Sweep Curve option. First, select the circle and press Enter, then select the helical curve and press Enter again. As you can see, we now have a helical shape with a defined thickness. The next step is to design the connecting sections of the antenna. Go to the Modeling menu and define a sphere shape to connect the design sections. Follow along with my demonstration. After that, we'll define the ground plane for the antenna. Again, go to Modeling and create a ground plane as I do. Now, let's start designing the coaxial cable. The first part is the inner pin. To create it, go to the Modeling menu, select Cylinder, and define it accordingly. The second part is the dielectric material, which will be Teflon. Let's design it. You can find Teflon material in CST's material library under the name PTFE. Finally, we'll design the outer shield of the coaxial cable. Once the coaxial cable is complete, we need to subtract its footprint from the ground plane. Select the ground plane, go to the Boolean menu, and choose Insert. Then, select the dielectric material. Now, the dielectric is properly inserted into the ground plane. Next, we'll define a waveguide port to excite the coaxial cable. Press S on your keyboard, select the Teflon material, and go to the Simulation tab to add the waveguide port. Click OK to complete this step. Before running the simulation, we'll define the frequency points for far-field patterns in the Field Monitor section. Set the range from 1 GHz to 3.5 GHz with a step of 0.1 GHz. Then, go to the Simulation menu, set up the solver, and start the simulation. Once the simulation finishes, you can check the return loss by clicking on the S parameters folder. To see the far-field radiation patterns, go to the far-field folder, select a frequency point, and view the realized gain in 3D. Since our antenna generates right-hand circular polarization, make sure to select the right option in the polarization settings. Now, let's move on to designing the quadrifilar helical antenna QHA. First, save the current helical antenna design and create a copy named QHA. This allows us to keep the original simulation results intact. Open the QHA file and adjust the dimensions in the parameter list to match the specifications for a quadrifilar antenna. To create the QHA structure, select all components except the ground plane. Then, go to the Transform menu, select the Rotate option, and rotate the components around the Z-axis 3 times. As you can see, we now have a quadrifilar structure. Next, subtract all the coaxial cables from the ground plane. To do this, select the ground plane, go to Boolean, and choose Insert. Select all the coaxial cables and press Enter. After that, define waveguide ports for each coaxial cable by selecting the Teflon materials and using the Simulation tab. At this stage, you have a fully parametric QHA antenna. You can adjust dimensions, such as the number of turns, and the geometry will update accordingly. Run the simulation and check the S parameters folder to review the results. In the S parameters folder you can see the S parameters of QHA antenna. For the far-field patterns, go to the far-field folder and select a frequency point. To simulate the combined performance of all helical arms with a 90-degree phase difference, go to the Post-Processing tab and select Combine Result Options. Enter the amplitude and phase values for each antenna element and click Combine. You can now view the combined S parameters and far-field patterns. Since this antenna generates right-hand circular polarization, select right in the polarization settings to see the realized gain. And that's it. In this tutorial, we've explored the design process for both helical and quadrifilar helical antennas, covering theoretical background, step-by-step design, and performance analysis. If you found this tutorial helpful and want to learn more about antenna design and RF engineering, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. We regularly post tutorials, tips, and insights into cutting-edge antenna technologies. Thank you for watching, and I hope you now feel confident designing your own antennas using these techniques. See you in the next tutorial.